This time we are looking at the improved Euler's method. From the given initial value problem, dy by dx, which is the function xy, and the initial condition y at x0 equals y0, with the step size h. The iterative formula for the improved Euler method is ym plus 1 equals yn plus h times k. K is the average slope or the average of the k1 and k2. K1 is found by using the slope function or the f of xy. X and y, they are the order pair at the current step. And un plus 1, this is called the predictor. If you recall, this is exactly the next step of the Euler's method, but we are going to use it as a predictor to get the corrector. So we name it as un plus 1, which is from yn plus h or step size multiplied by the k1, which is the slope that we just compute, and use un plus 1 as a predictor to find the slope at the next step point we call k2, and k2 is the function at xm plus 1 and un plus 1. And then we're going to use k1 and k2 to find the average, which could call the k, or k is a half of k1 and k2. For the graphical way, you start at the current step or xn with the Euler method. We're going to get the predictor, which is un plus 1. And next, we're going to find the corrector and the slope at the collector point here is the K2, where the K1 is the slope by using the original Euler point. And then we're going to find the average of K1 and K2 to get the actual point using the Heun's method or the modified Euler's method. We're going to work on the example using the improved Euler method to approximate y at zero point 0.2 using the same initial value problem. dy by dx equals x plus y, and the initial point is 0, 1. So make a list. So fxy is x plus y, x subscript 0 is 0, y subscript 0 is 1. Using the improved Euler method, the formula is ym plus 1 equals yn plus the h or the step size multiplied by k, where our k is a half of k1 and k2. So we have to work on a little bit more computation than the normal Euler method. At n equals 0, we already got x0, y0 from the problem that provided to us. Next, we're going to work on the next or the first iteration to get the y1, which is from y0 plus the step size. Recall the step size for the same example is 0.1. So the h is 0.1 multiplied by k. On the side here, we're going to find k1. K1 is the slope that compute by using the x0, y0, or the function at 0, 1. Use the formula as fxy is x plus y. So we get the k1 equals 1. And then we're going to use the predictor, which is u1. u1 is the same as the computation as the regular Euler method. That means we can get it as y0 plus the h multiplied by k1. y0 is 1, the h is 0.1, the k is 1 from k1 is 1 from the previous computation. Now we get u1 or the predictor is 1.1. Next, we're going to compute k2, which is the slope using the predictor. The slope is the function at x1, u1, or the function at the x1, we call x1 is x0 plus 0.1 or plus the step size, which is 0.1, where the u1 is 1.1 from the previous calculation. So we get k2 equals 1.2. After we get k2, we can use k1 and k2 to find k, which is a half of the sum of k1 and k2, or the average of these two slope values, or 1 half of 1 plus 1.2. So we get 2.2 divided by 2 to get 1.1 as the value of the k. Then we bring it back into the problem. Now we know that k equals 1.1. We obtain the y1 equals y as y0 is 1 plus 0.1 multiplied by 1.1 to obtain y1 equals 1.11, and this is the y at 0.1, or the character which is called the approximation of the solution at x equals 0.1. For the next iteration, n equals 2, y2 equals y1 plus the h, or the step size 0, 1 multiplied by k. So we're going to start the process again. So the k1, which is the function at x1, y1, which is the function at 0.1, 1.11 from what we found earlier. And we get the k1 equals 1.21. And next, we get the next predictor, which is the U2. U2 is the y1 plus the h multiplied by k1. And we get the y1, which is 1.11 plus 0.1 multiplied by 1.21. Next, after we get the U2, which is 1.11 plus 0.1 multiplied by 1.21, or 1.231. We use the U2, which is called a predictor, to get the slope of this predictor. So the K2 equals the function at x2 U2, or the function at 0.2. We call the x2 is x0 plus 2 times step size. Step size is 0.1, therefore the x2 is 0.2, and the u2 is 1.231. Now we get k2, or the second slope, as 1.431. That gives us the k, which is a half of the sum of k1 and k2, or a half of 1.21 plus 1.231, which give us the value to, this is, sorry, 1.431 over here. Let's clean up a little bit, make it readable. So 1 half 1.21 plus 1.431, and the k comes out to be 1.3205. So we bring the k value 1.3205 to the computation for the y2. Then the y2 equals the y1, which is 1.11 plus 0.1 multiplied by 1.3205. And we get the y2 as 1.24205 if we want 4 decimal places. So we have 1.2421 as the approximation y at x equals 0.2. And next we're going to complete the table. As you see, the column here is from the Heun's method, or from the modified Euler's method. The y at 0.1 is 1.11. The y at 0.2 is 1.2421, where the actual value from using the equation, or the function y equals negative x minus 1 plus 2 times e to the power x. Then we get y at 0.1 as 1.1103, and y at 0.2 as 1.2428. Compute the absolute error. which is the difference of the approximation and the actual value. The percent error at the first iteration is 0.027%, and the next iteration we get the percent error at 0.056%. If you compare with the table that we obtained from the original Euler's method, the percent error for the approximation from the Heun's method or from the modified Euler is less than the percent error from the Euler's method.